Hello everyone, welcome back to my channel Beyond Future. The topic which I am going to present today is free space optics communication. It's a very interesting topic, so let's go ahead. The contents of my presentation include the FSO communication, its block diagram, its benefits and challenges in today's world, and the different atmospheric channel models, and the FSO and polar coding, which we had discussed earlier, how it is related to FSO communication, and the simulation which we will perform. So what basically is free space optics communication? It is an optical communication technology in which data is transmitted by the propagation of light in free space, allowing optical connectivity. In layman's language, what we are doing over here is that regardless of regardless of the fiber optics cable or the different channels or the different mediums that we use to communicate our data through, there is no specific medium to communicate our data in FSO communication. What we are doing over here is that we use laser or visible light as our way to communicate with another person or to get our data from one place to another. The potential applications of FSO communications are extensive, from home to satellite. Even NASA uses FSO communication to transmit and to communicate with the spacecrafts that they send in the outside the Earth in the space. So this is a simple block diagram of FSO communication. What is happening over here is that at the transmitter we have laser modulator, driver, optical source, and the transmission telescope, which will transmit the beams of the data, having the data we are sending. And then there's the atmospheric channel, which is our biggest challenge, and you know that in atmosphere at anytime there is so much randomness. You can have the rain, you can have the fog, there's sunlight, there are clouds, and there's much more difficult uh, there are much more difficult implementations that we use, the models we have to copy these atmospheric channels. And then after the data moves through this atmospheric channel at the receiver, the bits are received via the receiver telescope. They go through the filtering, then the detection, then the amplification, and at the end they are demodulated and the data is stored in the computer or the device that you are using. So what basically are benefits of FSO communication, and why you should pay some of your why you should pay heed to this type of communication? This communication is faster, is securer, is lighter, and it's more flexible than most of the communications we are doing today. Just imagine 200 GB per second data rate is the data rate practically achieved from FSO communication, and it is more secure, which means no one can tap into it easily, no one can hack the data easily. The narrow beams make it impossible for the tapping of the data due to point and line of sight communication, and then these are have require lesser power and have less mass. The lesser power and less mass than the radio frequency communication system simply means that these can be easily utilized in our spacecrafts, and they are more flexible because we are not using fiber optics cable as a channel to send our data. The challenges, the most significant challenges we have in this communication system are basically the medium of transmission, which is air, vacuum, and so the atmospheric challenges here are much greater. There is turbulence, there is scattering, there is weather conditions that we have to take into account before we send our data through the channels. And then the atmospheric turbulent models, which are designed mathematically to study and mitigates the effects of the atmosphere, are mostly Rayleigh fading, the gamma gamma channel, Rician fading, Gaussian distribution, and much more. And just to add to the fact that attenuation and bit error rate is greatest in this model in the case of heavy fogs. So it is very difficult to implement this model of communication, but once we can implement this mode of communication, FSO communication, it can make life much easier because the transmission of data rate is fast. There is very low cost, in fact, and bit error rate could be mitigated if the we can easily and accurately modulate the atmospheric channels using the mathematical mathematical implementations we have for these turbulent models. So let's talk about the challenge. After the challenges, let's talk about the atmospheric channel models that are used to model the atmosphere and the conditions of the weather for sending our data. So there's the gamma-gamma turbulence model, which models atmospheric turbulence from weak to strong, which is based on two random gamma variables. What happens here is that gamma-gamma turbulence uh, models gamma-gamma turbulence model uses two random variables, which are basically gamma variables, but both variables are much different. One of the variable is used to model the smaller molecules or smaller variables, and the second is used to represent or symbolize the molecules which are great or which are bigger than those smaller ones. And what happens here is that this model basically use these two random variables and combines them to model the channel atmospheric channel, so that we can see how after sending the data we can receive the same bits or exact output, and how we can minimize the bit error rate during this transmission. In the Rician fading, what happens is that when one of the paths that is typically a line of sight signal or some strong reflection signal which is much stronger than other occurs between the path or the area through which we are sending our data. In Rayleigh fading, it is considered as the special case of Rician fading when there is no line of sight signal. It is also termed as molecular scattering. So, what is the relationship of FSO communication and polar coding? This is basically that the research in the field of FSO communication has always been very low. Since the invention of polar codes in 2008 by Erican, what happened is that this field, that is FSO communication, got a little bit of focus. This was because the polar coding could easily reach the theoretical Shannon limit, so to achieve the channel capacity. This made it possible to to implement FSO communication easily and to minimize the bit error rate. So what happens is that atmospheric turbulence and fading made it very difficult to practically implement these systems. But after the polar coding, what happens is the researchers are that research as the research indicates that polar coding has made it easier to implement FSO communication at longer distances practically, which was not possible before polar coding. There was the huge bit error rate. So these codes has the ability to mitigate turbulence and fading due to their greater error correction coding efficiency. So that's why FSO communication, the work is being done on polar coding and how to implement these codes in FSO communication. So let's go towards the simulations. The simulations in We have three simulations over here: the gamma gamma channel modeling, bit error for FSO communication, and bit error rate for polar coded FSO communication. So this is the gamma gamma channel modeling. Over here I have done the modeling for the strong turbulence channel. Over here you can see that as the normalized intensity increases, the PDF or the probability density function for gamma gamma channel decreases. The intensity is modeled from -20 dB to 200 dB. So as the intensity you can see is increasing, the disturbance or the probability density function for the gamma gamma channel model is decreasing. Over here, this is a simple bit error rate of FSO communication. Over here, you can see that for AWGN theoretical, bit error rate falls considerably for FSO communication as the SNR increases. You can check this and see this from the fact that the gradient is very steep. But in the case of Rayleigh fading, theoretically you can see that as the SNR increases, there is the bit error rate decreases almost linearly. And when we have simulated the same model, you can see that there is large variation. The system is too slow. As the noise is increasing in the system, bit error rate decrease at a very lower rate. So to mitigate these effects, to mitigate these kind of effects due to the noise we are having or due to the atmospheric modeling we are having, polar coding is being implemented in FSO communication. So work on FSO communication so far is the DSOC, which will be aboard NASA's Psyche spacecraft, which will utilize photons of visible light to increase spacecraft communications performance and efficiency by 10 to 100 times over conventional means. This means that the in 2020 and 2021, NASA is basically working on DSOC, which is a project which uses FSO communication, and the work is being done to increase this efficiency 100 times and to increase its performance also. So if you want to contribute in this project, you can go to the NASA's website and you can contribute because students are contributing in this area. And then there is another example of FSO communication, that is the practical implementation that NASA has done is it launched LADI in 2013, and there was a technology of optical communications which was used in it, and the bit error rate and its efficiency was measured in 2013 in FSO communications field so far. This is it for this presentation. I hope you enjoyed it. Thanks for watching. I will be back with more videos. Thank you.